This session, I would like to demonstrate another example on the use of a calculator block effectively to solve a problem. In fact, we've already considered this particular example while designing a CSTR or PFR in one of the previous demonstrations. I'm taking the same example for demonstrating this particular problem. The problem here is two CSTRs of equal volume operating at the same conditions 1150 Kelvin and 5 bar. To be used in series, what would be the minimum total volume of reactors in order to obtain a conversion of 90%? Now, because we have already done this problem, now I would like to demonstrate how to solve this problem using Aspen. So I'll go quickly because we have done this earlier. So define the components that are involved in the problem. These are the three components that we have. So go to the next step, choose a property model, go to the next step and simulation environment, try to draw your flow sheet. So we have two CSTRs operating in series. So let me create those two and connect input and output streams. So having drawn this flow sheet, now we will go ahead to define the problem statement. So let me change the unit system to SI. We know the feed is coming at 1150 Kelvin at a pressure of 5 bar. And the pure ethane is entering at the rate of 1 kilomole per second. This is same as what we have done even earlier. So go to the next. So we are now talking about the first reactor model, which is also operating at 5 bar. Same as the conditions of the input, 1150 Kelvin isothermal. Remember this. So by default, when you are talking about the reactor block, the valid phase of vapor only. Now anyway, for this reaction at this pressure and temperature, it is in vapor phase. Remember, this reactor model being operating in rating mode, we need to assume the volume. So let me make an initial guess of 1 cubic meter for the volume of the first reactor. Go to the next step. So we need to define the reaction. So it is labeled as R1. And we need to choose the kinetic model to represent this reaction. I am taking power law because it is given as elementary and reversible. So it's a first order irreversible reaction. So go to the similarly define the second reactor, which is also operating at the same conditions as that of the first reactor. 5 bar and 1150 Kelvin. So again, I am assuming the volume of the second reactor also as 1 cubic meter. So go to the next step. Now this is the reaction I am going to select. So next. So we need to now define the stoichiometry and the kinetics. We already know this stoichiometry. It is irreversible and first order with respect to C2H6. Whereas the exponents will not be coming into picture because it is irreversible. So this is the reaction stoichiometry. Now we need to provide the kinetic information. Remember here, the valid phase, reacting phase is by default liquid. So you please convert it into vapor. So at both places, you need to talk about the same phase. Otherwise, there will be a discrepancy and you may not be able to get your results. As you know, the frequency factor or pre-exponential factor or the rate constant should always be specified only in SI units. We have been given with this value 0.072 seconds to the power of -1, this being a first order reaction at 1000 Kelvin. And the activation energy for this reaction is specified as 82 kilocalories per gram. So we have specified the kinetic information, all the required input is complete. So let us go to the next. Remember, by assuming the volumes of both the reactors as 1 cubic meter each. Look at the stream summary. Of course, you can also observe the other results. What we are interested in obtaining here is a 90% conversion. As you can see, 1 kilomole per second of C2H6 is entering. At the end of the first reactor, we got a conversion of 37%. Conversion is FA0 minus FA divided by FA0. So this value will be indicating the conversion. And similarly, at the end of the second reactor, we were able to get a conversion of 58%. But according to the problem, we are supposed to obtain a conversion of 90%. So we know how to handle this, especially using rating models. So we'll be able to make use of design spec to get the required conversion of 90%. Now I'm dealing with this, of course, we have demonstrated this earlier because FNR is 1 and if 90% conversion of ethane has to happen, I will be able to know what is the molar flow rate of ethane at the exit of the second reactor. So 90% converted, so FA is equal to FNR into 1 minus XA. That means the flow rate of ethane at the exit of the second reactor should only be 0.1. I would like to read the conversion in terms of the stream flow rate. Of course, if you want, you can also define conversion by defining rate, outlet flow rate, and define the conversion. This is from the exit of the second reactor. The component is. Now, what should be the spec? Remember, we are indirectly measuring the conversion through the flow rate, which should be equal to 0.1, and the tolerance is 0.001. So how will you be able to achieve this conversion? Remember, by assuming the volume of both the reactors as 1 cubic meter each, we were able to get a conversion of 58%. So we need to increase the volume of the reactors. So one of the problems with the design spec is we will be able to only one variable. So I have chosen to vary the volume of the first reactor. Unfortunately, we will not be able to vary the volume of the second reactor in design spec because it will not allow us to vary more than one variable. So let's assume the volume of the first reactor is being varied from 1 to 10. Or you can even give a large value, let's say 100, doesn't matter. So having defined this, now let us run the problem. I'm trying to address this problem in steps. So instead of addressing all the issues at once, as you know, for every design specification, secant method is the default method used by Aspen, and within 9 iterations, we were able to come to a convergent solution. Let us look at these results. So when the volume of the first reactor is 1, we got a conversion of, the flow rate of ethane at the exit of the second reactor is 0.41. But when the volume became 13, it has come to 0.1009. 1 kilomole is entering, so the conversion is 90%. So what is the total volume of both the reactors that we got? Remember, the volume of the second reactor was constant at 1 because we are varying only the volume of the first reactor. So the answer for this problem is 13.52 plus 1, 14.52. But the issue here is, this is not what we exactly require. We wanted to use CSTRs of equal volume. How can we do this? See, the problem with design spec is at the maximum you will be able to vary only one variable, right? And we got to a total volume of about 14 cubic meters. How are we going to make sure that this is? We did not address that problem. But we know theoretically when we are conducting a first order reaction in two CSTRs connected in series, theoretically we have derived an equation stating that unless and otherwise these volumes are equal, the performance is not optimal. So this theoretical result you can verify from your reaction engineering course. Now, whatever limitation that I have of varying only one variable in design spec, now I would like to overcome that by using a calculator block. So save new, right? Then I'm going to define, let us say V1, which is the volume of the first reactor. Block variable. Block is V1, variable is volume in cubic meters. Similarly, I would like to define volume of the second reactor as V2. It's also a block variable. Block is now V2. Variable is volume. Remember, in the case of design spec, we are varying the volume of the first reactor. Now, I would like to vary the volume of the second reactor equal to the volume of the first reactor. So what the calculator block needs to do it will import the information about the first reactor and equate that to the volume of the second reactor and export the volume of the reactor to Aspen for implementation. Right? So I am reading the value of volume from Aspen, do something in the calculator block, export the volume of the second reactor to Aspen. So let us go to the next step. As you can see, you can use either Fortran or Excel. Now, should I write V1 is equal to V2 or V2 is equal to V1? We should write V2 is equal to V1 because we are reading the value of V1 from Aspen, making it equal to the volume of the second reactor and export it back to Aspen. So with this calculator block, you can see what is it doing? It is reading information. It is taking volume of the first reactor is manipulated by the design spec. That value is communicated to the calculator block, and this value of volume is equated to the volume of the second reactor and is exported back to Aspen. Let us see after running this problem. So again, within 7 iterations, we were able to get to the convergent solution. Let us look at the results. So as you can see, we were able to get a total conversion of 90%, or the flow rate of ethane in the exit is again 0.01, sorry, 0.1. And what is the volume of the first reactor? 4.72. And we need to know what is the volume of the second reactor. So let us look at the results. Okay, I will not be able to see here. So we already know the volume of the first reactor. Let us see the volume of the second reactor. So again, you can see it is equal to the volume of the first reactor, which is 4.72518. So what is the total volume of the two reactors required to obtain 90% conversion? 2 into 4.72, about 8.44 roughly, or 45. So this is the minimum total reactor volume required to obtain a conversion of 90%. So what we have done in addition, whatever limitation we had in this of not able to vary more than one variable is now being overcome by incorporating this calculator block. So like this, we have seen earlier the splitter model, which doesn't have any logic. We were able to incorporate that logic into the splitter model using a calculator block. So like this, you should be in a position to employ wherever necessary the use of a calculator block.